All right, everybody. Now that you have done a good review of all of your exponent rules, we're going to talk about what an exponential function is. So basically, when you look at an exponential function, the thing that sets it apart and that makes it its own little class of family or family of a function is that when you see it, the variable is in the exponent, okay? So it's going to look different than other functions that we've had. For instance, we've done y equals x cubed, right? Where the x, the variable, is down in the base here, right? That's not the same. This is just a cubic function that maybe looks something like that, depending on how much it bounces around, how much stuff's added to the backside of it and stuff like that. But it's just an S-curve. These are going to have their own very special shape, and they're going to have their own behavior, and we're going to try to look at them in groups of exponential functions so that we can talk about exactly what's going on when we see this happening. So we're going to approach this just like we would approach just about any of our functions whenever we're given them. And we're going to put in some point values. And I like to usually do one or two positive numbers, 0, and one or two negative numbers. Now, we're not always going to do all of these, but I want to give these at least to kind of give us an idea of what's going on here. So whenever we do this, I'm going to just plug these numbers in. These are my x values. So it'll be like y equals 2 to the first, right? When x equals 1, I'll plug in 1 for x, to y equals 2 to the first. Well, we know that that's just a 2, right? Y equals 2 to the first is a 2. So we're going to have the point on our graph 1, 2. Okay, x equals 1, y equals 2. So just kind of running through that real quickly. If I put in a 2 for the x, I'd have y equals 2 squared. And we know that 2 squared is 4. So when x equals 2, y equals 4. Okay, that's another point that'll be on my graph. And one more on the positive side of things here. Y equals 2 to the, what if x is 3? 2 to the third, right? 2 cubed would be 2 times 2 is 4 times 2 is 8. So that would be an 8. So we're going to have the point 3, 8 on this particular graph, where the base in this function is the 2. Okay, the exponent is the variable. And then we have to use some of those exponent rules that you just got finished, working through. So hopefully you've watched that review video, and it's y equals 2 to the 0 is the next guy right here. And what happens whenever we raise anything to a 0 power? Doesn't matter if it's a 2, a 5, a -3, whatever. Anything to the 0 power is a 1. Right? And if you don't remember why, go watch that review video because I spell it out in black and white exactly why we will get a 1. But it doesn't matter. This could be pi in here. Y equals pi to the 0, and it's a 1. Okay, so we're going to have this point 0, 1. And then I've got these negative things. So again, hopefully you have watched the review video on exponent rules, because when you do, you'll see, hey, when I raise something to a negative exponent, I don't like having negatives in my exponent. So what I'm going to do is I'm going to make this positive, and the way I do it is by moving this whole entire thing to the denominator, 2 to the first. So, and when I do that, this negative, when it goes to the bottom, that negative exponent becomes a positive. Negative exponents become positive when you move it to the denominator. Okay. So you have to be careful with this though, because it's the negative exponent that gets changed here. So the -1 was my exponent. When I move that to the bottom, it becomes 2 to the first. The only thing that is changing is the exponent from negative to positive. So if this was -2 out here, then the negative would still be there. It's only the exponent that's changing. And then the thing was, when we move that to the bottom, what goes on top? We've got to have a place filler, right? Well, it's a 1. So when I raise 2 to the negative 1 power, I get a 1/2. And again, on that video, we did a lot with it to show what's going on there. But just to make sure your calculator confirms it, 2 raised to the negative 1. And sure enough, it says it's 0.5. Okay. So that is how I get 1/2 or a fraction out of that. Okay. So when you raise something to the negative exponent, we invert it, we flip it to the bottom and change the exponent to a positive. So one more, and hopefully you can run this one real quickly on your own. What if x is -2? That'll be 2 to the negative 1/2. So think through that for just a second. The negative exponent, if I move it to the bottom, the negative exponent becomes a positive, right? And I'm going to have a 1 on top. So this becomes 1 over 2 squared. But we know that 2 squared is 4, right? So 2 squared is 4. So this 1 over 2 squared is 1/4. Or 2 to the negative 2 is 1/4. So 1/4. So what we see here is that we've got some powers. As we get bigger on the positives, it's getting big. And as I get bigger negative numbers, so negative integers, so smaller actually, but as the absolute value of that gets bigger, I get these small fractions. So what's going to happen whenever I start to graph these points? And this is a basic idea for what happens anytime I'm looking at exponential functions. So we'll get some, oh, we see this property is going to happen, this property is going to happen. But let's just kind of get some of these points in there and see what we see. So here's my x, here's my y. I've got 1, 2, 3, 1, 2, 3, and I've got -1, -2, and I'll go ahead and stick a -3 there. And going up, I've got as high as 8, 2, 4. Let me get some extra points in there. 5, 6, 7, 8. Kind of squish them together a little bit. Sorry about that. All right, so I've got the point x equals 1, y equals 2. So over 1, up 2. 2, 4. Should have just counted by 2's to begin with. Over 1, up 2. That's what's going on there. And I've got the point x equals 2, y equals 4. So that's right in there, right? And I've got the point x equals 3, y equals 8. So that's way up there. So that's all of these. I've got those 3 positive guys. I've also got the point 0, 1. So none on the x-axis, up 1 on the y. Okay, so 0, 1, that point is going to be important for us. And then -1.5, -2 1/4. If it had been -3, it would have been -3 and -3 and 1/8, because it would have been 2 cubed on the bottom, right? So 1/8. And what we know is here's 0, 1, here's a half that's smaller. A fourth is smaller than a half. An eighth is smaller than a fourth. So what I see happening here on the bottom is that it's getting closer and closer and closer to this x-axis, which we're about to see is going to be a horizontal asymptote. My question is there anything that I can raise? Remember, I'm here. Raise 2 to a power that will give me a 0. Anything that I can raise 2 to some power that'll give me a 0. And the answer is actually no, because the only special case there is what if that exponent is a 0? We already know that's 0, 1, right? So what happens is these fractions on the small end, on the negative end here, the fractions just keep on getting smaller and smaller and smaller, but they never actually are equal to 0. So that's that asymptote idea going on. So I'm going to have a horizontal asymptote at y equals 0, okay? And that was a pretty common one whenever we were doing asymptotes. Y equals 0, it's going to come in there, okay? So I've got a horizontal asymptote. It's not going anywhere. It's just going to be right there. And then I say, okay, what is going on with like all of these things? So we're going to do a different example, and then we'll see how they compare. So hold that thought, because sooner or later, you're going to want to do what we did whenever we were using parabolas and different functions is we're going to want to start shifting these and stretching these and doing other stuff to them. But we got to have in our mind what the basic parent function looks like. What is this family going to look like before I start shifting it? So that we know, okay, we're start here and then we start moving things around, okay? And then we can apply all the rules that we had back in chapter 1 and 2, basically. Or I guess it was chapter 2. So here, let's do this guy. Y equals 3 to the x. Okay. So it's very similar to the one we just did. The other one, the base here was a 2. This is a 3. So we're going to talk about what that graph looks like. We're going to put some points up. So X and Y. I'm not going to do quite as many points. I'm actually only going to do 3 because I feel like if you do a 1, a 0, and a -1, that will give you a pretty good look if you know what you're looking at. So if I had Y equals 3 to the first, that would just be what? 3 to the first is 3. Okay, so I'd have that point, 1, 3. If I had Y equals 3 to the 0, we already know anything to the 0 power is a 1. So that's going to be 0, 1. That's an important point. We'll see it come back over and over and over again. And if I had Y equals 3 to the -1, remember your negative exponent rule. This puts the entire thing on the bottom, 3 to the first, and makes that exponent positive instead of negative. And then on top, we get a 1. So that's what's going on whenever we start plugging things in. 1/3 there. And if you want more points, you can do more points. I'm just trying to get a rough sketch of what this guy looks like because we're going to see similarities whenever we start talking about this guy versus the one we just did a second ago. So here we go. Here's my X, here's my Y. I'm only doing 1, 0, and -1 for my X's, and I need to go all the way up to 3 for my Y values. So 1, 2, 3. And go ahead and graph it on your own. You can pause the video, whatever you need to do. This point is 1, 3. So 1, 3 is up here. This point is 0, 1. So that guy is my y-intercept right there. And this guy is -1 and 1/3. And if we think about it, what would happen if I raised 3 to the second? Well, that would be 9. 3 to the third would be 27, and 3 to the fourth would be 81. So on the positive x's, this is just going to shoot up, right? Just goes up, boop, really fast. And what would happen if I was doing all the negatives? So if it was -2, I get 1/9, which 1/9 is smaller than 1/3. And if it was -3, I'd get 1/27. And if it was -4, I'd get 1/81. So over here, sorry, I had to pause it real fast because I was about to sneeze. Sorry about that. I was trying not to sneeze in anybody's ear. I hope I caught it fast enough. Paused it so that it wouldn't sneeze in you. I wouldn't sneeze on you. But anyway, these just keep on getting smaller and smaller and smaller fractions. So what we see is the same idea of we're going to have a horizontal asymptote right there, right? At y equals 0. Okay, so let's look. Here was my 2 to the third. I'm sorry, 2 to the x over here. Y equals 2 to the x. Here is my y equals 3 to the x. And I'm feeling like we see some similar stuff. Both of them have this point 0, 1. This point is 1, 2, whereas this point is 1, 3. This point is -1, 1/2, whereas this point is -1, 1/3. So I feel like those points look really similar. They're just changing based on what the base here is, right? A 2 versus a 3. Here it's a 2, here it's a 3. Here it's a 1/2, here's a 1/3. So they're very similar. They're just going to change based or determined by what your base is, okay? Try not to use that word base too much because in this particular chapter, base really means something. Here, the base is 3. The exponent is an x. Okay, so, and these, again, what is an exponential function? Exponential functions have x in the exponent. Or it doesn't have to be x, but whatever variable I'm working with. If we had an equation that was like based on the variable t, then it would be a t in the exponent. So it's whatever my f of whatever. So here, these are functions of x. So I'm going to talk about x. Okay, so here's some always stuff, and that's unusual. We don't have tons of always in this class, but here's what it looks like. For exponential functions, where b is greater than 1, y equals b to the x is what we're talking about. That's my, b is my base. Okay, well, we got something like this. Y equals b to the x, and b is greater than 1. We'll talk about other cases in a little bit. Okay, but where the b is greater than the 1, we're going to have these things happen. Number one, we always have a horizontal asymptote. Remember, I abbreviate that HA at y equals 0. And remember that this is all happening with the very base function, 3 to the x, 2 to the x, pi to the x, 5 to the x, 10 to the x, whatever it is. Okay, this is not happening once I start moving things around, right? So this was horizontal asymptote. Okay, so it's not happening once things start moving. Once things start moving, if you shift this graph around, the asymptotes shift with it, and the points that I'm going to talk about will shift as well. But for the original, before I start moving things going around, we're always going to have that horizontal asymptote at y equals 0. Number two, we'll always have a point. And again, you don't normally hear me say always, but we always have the point 1 and the base, or 1 comma b, okay? Because we're saying b is base, right? So again, this is because any number that I raise to 1, the power of 1, is going to give you back that number, right? So this is an always kind of situation. Number 3, we always have the point 0, 1. And again, that goes back to my exponent rules. Anything to the 0 power is always a 1. We don't have to worry about it. That point is always going to be there. And the fourth one is we always have the point -1 and 1 over the b, or -1, 1 over the base, whichever way you want to think about that. Okay, and again, that is because of the exponent rule. These are rules. Rules mean they are always true. So, and write yourself a little note if you need to, wherever, whatever this is before any transformations. Okay, so of course, if I shift all of the whole entire graph up 5, well, it's not going to be 1b anymore, right? It's going to be 1b plus 5, whatever, if I shift it all up. So that point will shift with the entire group or graph whenever I shift the thing around. So those points are always is, okay? So that is basic stuff that happens whenever b is greater than 1. I think of these as my positive whole numbers. What if I had pi 3.14 that's greater than 1, stuff like that. But the question sometimes comes up, what if b is a fraction between 0 and 1? What if b is a fraction? All right, well, if b is a fraction, then we're going to have a slightly different case that happens there. So let's talk about the graph where y equals 1/2 to the x. Okay, and we're going to approach this the same way we did the other one just a second ago, which is to make points and we'll say, what if x is 1? What if x is 0? What if x is negative 1/2? Okay. Well, what if x is 1? We would have, let me plug it in. Y equals 1/2 to the first. Well, what's that? It's 1/2. Okay, so basically, because I'm starting with a fraction, instead of whole numbers or big positive numbers and shooting up to the right, I'm going to have a fraction there because I'm starting with a fraction, right? What if x equals 0, so y equals 1/2 to the 0? Well, anything to the 0 power is a 1. Done. Okay. And what if my x value is a 1/2, or I'm sorry, a negative 1? Okay. Well, that means I'm going to flip this guy, right? I'm going to rotate it. But what happens there? The 1 will come to the bottom, the 2 will go to the top. So this is going to become a 2. So basically, whenever I'm looking at the negative numbers, I'm getting the big positive numbers. Whenever I'm looking at the positive numbers, I'm getting the little bitty fractions. So it's going to end up being a reflection around the y-axis is what this is whenever you're talking about your fractions. So looking at that graph, so we can see a good idea of what it looks like. X is here, y is here. We're going to put in 1 and negative 1. If we need more points, we'll go with it. Okay, we're going to have the horizontal asymptote just like in the others, y equals 0. Okay, but here what's happening is 1, 2, 3. Here what's happening is when I put in the positive 1, I get a 1/2. What if it was 2? 1/2 squared, well, that would be a 4th, right? So that would be smaller. And if it was 3, that would be an 1/8. So see, we're still getting those fraction things. They're just on the right-hand side now instead of the left-hand side. And what about the negative 1? Negative 1, 2. Oops, I left off 0, 1 right there. Okay. So, and what if it was negative 2? Well, it would flip it and it would be 4, right? So it's going to shoot up. If it was negative 3, it would be 8 and so on. So you're going to get the same look of the graph. It's just that on the right-hand side, I've got fractions, whereas when when the base was bigger than 1, the fractions were on the left-hand side. So basically you can see these are inverses, or not inverses. These are reflected is the word I'm after around the y-axis. So that's what's going on there. If it was bigger than 1, it goes up to the right. If it's a fraction between 0 and 1, it goes down to the right. Okay, so those fraction guys, they just look a little bit different is what happens. FYI, right? All right, so that's the basic idea of what's going on here. Later, we'll talk about, well, what if we have a negative out in front? Well, that's going to reflect it, right? What if we do this? What if we do that? So those transformation things that we've all dealt with before, they will come back in to come back around, okay? So I want to talk about how we might use this. So there is an example that's in the book that says, hey, what if you have a function and it's 42.2 times 1.56 to the x value. And they tell you that this models average money spent at a mall, models average amount of money spent at a mall after so many hours. Okay, so in other words, if you are at a mall and you hang out 1 hour, 2 hours, 3 hours, how is that amount that you spend at the mall increasing? So this is a growth model after so many hours, and where the variable is in the exponent here, and the variable is the number of hours that somebody spends at the mall. Okay, so this is just an example they gave you, and they said how much on average is spent after somebody has been at the mall 4 hours. Okay, so this is the idea of, can you take this function and can you utilize it to get me an answer? So I hope you can. It's just like any other function. They want to know 4 hours. So what are you going to do? Plug in 4 everywhere you see an X, right? So what does that look like? F of 4 is 42.2 times 1.56 raised to the, instead of X. Yep, we're going to put in a 4. Okay. And then that just basically becomes calculator work where you have to know your PEMDAS. Please excuse my dear Aunt Sally. We're going to do the parentheses and exponent first. And then after we do that, we'll end up multiplying it, right? So here I go, 1.56. I'm going to raise that. Remember, you've got this little exponent button here that's right about above your division bar. That's the raise to button. It gives you an exponent. So 1.46 raised to the 4th is this big long decimal. Okay, I'm just going to hold that in my calculator and then I'm going to what? This operation is multiply, right? So multiply it by 42.2. Okay. And I am getting 249.93, basically. 249.93. And that was money spent, right? So what they're saying is at this particular mall, if you're there for about 4 hours, you're probably going to have spent about $250. Okay. So that's kind of a lot of money to be spending going in. Okay. All right, one more kind of application problem just to make sure that you know, okay, why are we bothering with these exponent stuff? Where is it going to come into real life and stuff like that? A very, very common place where we use these exponential functions is when we start talking about money spent, when we start talking about if you borrow a certain amount of money, what do you owe after a certain amount of time, that kind of stuff. One of the basic formulas for that is the compound interest formula. Okay. So the compound interest formula looks like this, and we'll talk about what they mean in a second. A equals P, parentheses, the number 1. You can write it like that if you wanted to, plus R over N raised to the NT. Okay, so we're going to talk about what all those things are. So let's go. So the A stands for amount. Okay, and basically I like to think this is the amount in my account at the end of whatever time I'm leaving it there. So if I put money into, say, a checking account or a savings account or whatever, at the end of so much time, whatever that is, the A is how much money will be in that account. You can also use this formula, say, if you're borrowing money on a credit card or something like that. You just have to figure out how to use it. Okay. P is the principal amount. Principal amount. Okay, what the heck does principal mean in this case? It's the initial amount. So again, if I'm putting money into an account, then this is the amount I put in. So say I decide, hey, I'm going to hold back money for a truck I'm going to buy or something like that. And what I'm going to do is I'm going to put $5,000 into a bank account and I'm going to let it sit there and draw interest so that at the end of, I don't know, 5 years or something like that, maybe I'll have a really good down payment so that I can go buy a car or a truck or whatever it is I'm after. Okay. So that's the principal, the amount that I put in at the beginning. It could be a loan, it could be that I take out money, it could be a checking account that I put in money. There's lots of ways to use this formula. Okay. The 1 is the number 1, so we're not going to do anything with it. The R is the interest rate. R is for rate. Okay. But in this case, it's always going to be an annual interest rate. So we may have to do some stuff to adjust it. Also, remember that normally when we talk about, say, interest rates, they may say it's a 6% APR is what they say, annual percentage annual percentage rate. Well, I can't use 6% inside of the formula. So I'm going to have to change this, and I'm going to have to make it into a decimal. So remember that the decimal is sitting at the back here, and percent means per 100, and 100 is 10, 100, 2 decimal places, right? So the thought is you move the decimal place 2 points to the left to get a decimal instead of this percentage. So when we use interest rate in the formula, we are going to make sure that we use a decimal, not the percentage, whatever that is. Okay. So I'm going to use this N here, and I'm going to tell you that this N and this N are the same N's. So let me come out here. N stands for number, and it's for number of compounds. And because our interest rate is in years, annual, this is going to be number of compounds per year. Okay, so again, think about that. If it says it compounds once a year, that's a 1. If it says it compounds monthly, how many months are there in a year? 12. So then my N would be a 12. If it says quarterly, how many quarters are in $1? There are 4 quarters in $1, so then your N would be 4. So you're going to have to read the problems and be really careful with what it tells you. All right, and the last variable is T, and probably most of you know T stands for time. And again, this is time in years. So everything needs to be in years when I work it through, okay? So what does that mean? If it says it compounds monthly, if it says that it's for 4 years, then I'm going to say, okay, fine, T is 4. But if it says we're only going to leave it in there for a half a year, okay, or if it says 6 months, we don't use 6 for the T because that would mean 6 years, right? So if it says 6 months, then we're going to use 1/2 because that's half of a year, okay? So we may have to do some stuff to play with it and make sure we can use it. But that's the basic formula. And that's what all the variables mean. So if you need to pause for a minute and write down, okay, what is this variable? What is that variable? Go ahead and pause or do whatever you need. And then we are going to work a problem. And that'll be the last thing for this video. All right, so hopefully you've got everything you need. Our example says, okay, this is a real world kind of usage of this formula and why we would bother with these exponential functions to begin with, okay? So the example says you want to invest $8,000 into an account paying 7% in annual interest rate, but it's going to be compounded monthly. Okay, that's what we want to do. We're going to leave it for 6 years. And the question says, how much money will there be at the end? And I'm going to tell you, it may take you a couple of extra seconds to do what I'm about to do, but I really think, especially if you get confused with your variables, you need to take a minute and come off to the side and say, what are the variables in this function? A is the amount at the end. Well, it wants me to know how much is at the end. So that's actually what I'm looking for, right? Which is kind of nice because my function's already, or my formula's already solved for A. Okay, P, we need to find out our P. What's the P? P is the principal amount, the amount that I'm going to invest at the beginning here. So how much was that? I'm reading this, I see that P is $8,000. So fill it in. Make yourself a little table over here and fill this stuff in. What's your next variable? R. Well, what does it say my R is? That's my interest rate, 7%. Okay, but don't you dare try to put 7% into that formula. Remember that we've got to make that into a decimal. That's 0.07 that I'm going to use in my formula up there. Okay, what's the next variable? N. N, remember that's the number of compounds per year. What's it say? It says 7% compounded monthly. How many months in a year? 12. Good. And the last variable is T, which we know stands for time in years. And it said I'm going to leave that for 6 years. Okay. So it took me a couple of extra seconds, I know, to make this little grid off to the side. I didn't need that much space, but whatever. Okay. It took me just a couple of seconds to write all that out. But look, I've got all my variables put off here, and I know I'm solving for A. So when I go to rewrite this formula, I'm going to say A equals, that's what I'm trying to find. And the formula was P, well, that's an 8,000, parentheses, 1 plus, the R goes on top, well, we said that's 0.07. The N goes on the bottom, divide by 12. Okay, and then up here in my exponent, I've got N times T. So we just said N was 12 and T is 6. Look how smoothly that gets substituted in when you take just a second and write out to the side what each of your variables is. I think it's worth it to take that second and write it out, especially if you tend to get confused. So here we go. That's my formula. I'm going to work it out. If you want to pause me for a second, go ahead and do it on your own. That's fine. Okay. I'm going to do 2 things here. The first one is I'm going to remember my PEMDAS, and PEMDAS says I need to do all this stuff in the parentheses, and then I need to mess with my exponents, right? So inside of the parentheses, 1 plus 0.07 over 12, what do I do first? I divide first, right? Because PEMDAS, multiply and divide, comes before adding and subtracting. So multiply or divide first. So that's a 0.07 divided by 12. Oops, sorry, it's got a glare. That's 0.00583, and then add your 1. So I'm doing everything inside the parentheses. 1.0058. I'm going to stop there, but I'm going to keep that decimal in my calculator so that I can play with that in a minute. Okay. And then up here, I've got, I'm sorry. Up here, I've got 12 times 6, and that is 72. So I can go ahead and do that because that's just simplifying the exponent, right? It's not doing anything else. And then what I need to do is I need to raise this 1.058, blah, 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 this long decimal I have. I'm going to raise it to the 12 times 6 or 72, and that's what I get. So it's next thing I do is take care of that exponent. So remember your order of operations, remember PEMDAS, 1.058, oops, sorry, raised to that power is 1.525201, dot, 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 dot. And again, keep that decimal in your calculator because we're going to want that. Sorry, I messed up my thing whenever I made sure that it was 72. So I've got this big long decimal going on, 1.50201. I want all of this decimal stuff out here. So don't round. You don't round until the very last step. So then I multiply by the 8,000. What do I have? A equals $12,160. And hang on, we're going to round here. So it's 84.4. The rule is if this is a 5 or bigger, I would mark that 4 up to a 5. It is not a 5 or bigger, so $12,160.84. And we're going to 2 decimal places because this is an amount of money. Remember, I invested $8,000. They want to know what I got at the end of 6 years. The amount in the account at the end is $12,160.84. All right, so that hopefully gives us a really good overview of what the heck is an exponential function. And this is actually going to be a 2-part video. The next part, we will talk a little bit more about some of the other uses and start going into logarithms. So I hope this helps and talk to you soon.